Hi all, today we are going to discuss about low power factor wattmeter, which is also called as LPF wattmeter. What are the design parameters that are considered while designing the wattmeter for low power factor applications? So before going to this, let us see the prerequisites that are required for this lecture from the last two lectures. Because last two lectures we have discussed about how the dynamometer type wattmeter works and what are the errors that are introduced in wattmeter and how to overcome them. So those basics whichever are required from there I am directly taking here. So if you are assuming that the current that is passing in the pressure coil is in phase with the voltage, that means the pressure coil doesn't have any inductance, then we can see here the IP is in phase with the voltage. Let us assume current passing in the current coil is nothing but the load current that is lagging behind the V by some angle phi, that is power factor angle. So in that case the amount of the deflecting torque that is produced, that can be given by the current passing in the pressure coil multiplied by current in the current coil multiplied by cos of the angle between these two. In this case it will be cos phi into dm by d theta, or this value of the IP I can write as voltage divided by, because it is a across element, this will be V divided by Rp into this IC is nothing but I into cos phi into dm by d theta, or otherwise from this we can write this TD deflecting torque is proportional to V into I into cos phi. So let us assume if the value of the cos phi is very less, that means we are going for the case of low power factor. Low power factor case cos phi is less. When cos phi is less, what is happening to the deflecting torque? Deflecting torque is decreased. When deflecting torque is decreased, the pointer will not move so much easily. It cannot show the point, it cannot point properly. Okay, so this is the first one. So and second one, practically the inductance of the pressure coil cannot be neglected. So practically if this is V, the value of the IP that will be lagging behind this voltage coil by some angle beta. Let us assume the current passing in the current coil IC is nothing but equal to I. So this is making an angle of phi. So the angle between these IC and IP I am taking as phi dash. So in this case the amount of the deflecting torque that is coming, so that will be nothing but IP into IC into cos of the angle between them. Cos of the angle between them is cos phi dash into dm by d theta, or this I can write as IP is nothing but voltage divided by, because here it will be impedance. So impedance means it will have two parameters, one will be Rp, one will be XP, that means reactance of the pressure coil. This angle will be beta, so this will be ZP. So V divided by impedance of the pressure coil into IC is nothing but I cos, what is phi dash? Phi dash I can write as phi minus beta. This is phi minus beta into dm by d theta. So this we have simplified in the last class, so I am directly writing the equation, final equation what will come. That final equation we got there as this TD is equal to V into I into cos beta into cos of phi minus beta into dm by d theta. So how this came? The value of the ZP, because from this equation cos beta is adjacent by hypotenuse, adjacent is Rp by ZP, or otherwise the value of ZP I can write as Rp divided by cos beta. This is nothing but Rp divided by cos beta. So when you substitute it here, so this will come as V into I into cos beta into cos of phi minus beta divided by Rp. So this term will come, or otherwise we can tell the value of the TD that is proportional to, in this case, V into I into cos beta into cos phi minus beta. Here also again you can see it is depending on the value of phi. So under low power factor condition, as the phi is less, so in that case also the amount of the deflecting torque is affected. Similarly, we have seen in the last class the error that is introduced due to the inductance of the pressure coil, that is given by V into I into sin phi into tan beta. So here also you can see the error is depending on the value of sin phi. That means when the value of cos phi is less, that implies that the amount of deflecting torque is decreased and the amount of the error that is increased. The reason is if cos phi is less, that means sin phi is more. So we can tell that the error is increased. That means whether you take the ideal case or practical case, in both the cases we can see that whenever the power factor is low, the amount of the deflecting torque is decreased, and the amount of the error introduced, that means difference between measured value and true value, is very high. So that's why some design parameter changes are required in order to incorporate them. So let us try to summarize what we have seen till now. So the observations that we made till now is that deflecting torque on the moving system is small because the deflecting torque TD is proportional to cos phi, or otherwise cos phi minus beta. Again, it is depending on phi, even when the current coil and pressure coil are fully excited. That means assuming V and I are constant compared to the normal type instrument. Then second one, the errors introduced because of the inductance of pressure coil that becomes very large at low power factor, because error is proportional to sin phi. If cos phi is less, sin phi will be very high. So some special features are incorporated in the wattmeters in order to do this. So let us start with what are the different changes that are required. We know that our instrument will come to the final steady state position when the value of TC is equal to the deflecting torque. Agreed? So this value of the TC is nothing but some constant K1 multiplied by theta. What is this K1? This is nothing but spring constant. So let us assume this TD, I am writing some constant K2 times of V into I into cos phi. Let us take the ideal case to make it easy. Or from this I can tell the value of the theta is K2 by K1 into V into I into cos phi. So let us assume this top parameter, this is decreased. Why it is decreased? The reason is cos phi is decreased. So if you want to maintain the same angle even when the cos phi is decreased, how you can do it? By changing the value of the K1. That means what you have to do? You have to decrease the value of K1 such that this will be compensated. Or otherwise we can tell that you have to decrease the value of the spring constant so that even though due to low power factor the amount of deflecting torque is decreased, that will be balanced by decreasing the spring constant. That means the low power factor wattmeters are designed to have a small controlling torque so that they give the full scale deflection even for the low power factor as low as 0.1. Up to that much it will work. Then coming to the pressure coil current. So the pressure coil current, actually the pressure coil is designed to have some low value of the resistance. So because of that, what happens? The pressure coil current will increase. Let us see in order to understand this. Let us take the equation of the TD. So TD we have taken as IP into IC into cos phi into dm by d theta. This one what we are getting? So this value of this IP is nothing but V divided by RP. If you are taking the ideal case, this is I into cos phi into dm by d theta. This is what we are getting. So if you want to increase the dP, because here what happens? Cos phi is decreased. So to balance it, so what I have to do? Decrease the value of RP so that this will be balanced. So when you decrease the value of RP, what happens? V divided by RP, that will be increased, or the current passing in the pressure coil will increase. So that will balance the decrease in the deflecting torque due to decrease in the power factor. So that's why practically in the case of low power factor type wattmeter, what will happen? The pressure coil is designed to have a low value of the resistance so that the IP is increased. So that will increase the overall deflecting factor, or it will counterbalance for the decrease in deflecting torque due to decrease in cos phi. That is a basic concept. So practically in low power factor type of wattmeters, the current that is passing in the pressure coil will be nearly 10 times the current that is passing in normal type wattmeters, or wattmeters which are used for high power factor applications. So that changes are required. Then coming to the next one, compensation for the pressure coil current. So if you take the wattmeters, the wattmeter connection, because it is basically having a current coil and a pressure coil. So depending on how these are interconnected to the system or what location they are connected, there are basically two connections are possible. Your pressure coil either can be connected in the supply side, or your pressure coil can be connected in the load side. Let us see each case. So in this case, let us assume this current is equal to IS. Out of IS, here one current is passed, that is equal to IP. Here my load current, that means the IC is nothing but equal to the value of the current that is passing in the load. Same thing is passing. So now the voltage applied across your pressure coil, that will be the voltage across your load plus what is the voltage drop in this current coil. Let us assume this current coil is having some resistance RA. So we can tell that the value of the Vs, this is equal to V plus I multiplied by RA. That means the voltage that is measured by pressure coil is not equal to V. It is measuring the extra thing voltage drop. through the current coil. So this I am just summarizing here. The current passing through the current coil is I, and voltage across the pressure coil, that is nothing but Vs is V plus I into the current that is passing in the current coil. So let us take, instead of Ra, let us take it as Rc to avoid the confusion. I am just taking as Rc. So Rc. So from this I can tell that the measured value of the power, it is nothing but equal to true power. That means Vi into cos phi, that is happening across your load, plus it is measuring the loss in this current coil also, or power consumed by the current coil, that I am representing by PCC, or otherwise we can tell the total power is PT plus I square into Rc. So here you can see Pm minus Pt, that gives the error. That error is depending on the value of the current. That means in the case of low power factor case, for a given power, because if you are taking power P is equal to constant, if cos phi is decreased, then how it will balance? Because voltage is constant, your instrument will draw more current. That means under lagging power factor conditions, the current will be increased because of decrease in the value of the cos phi for a given power. So as the current is increased, so what happens? This error is increased. That means if you are connecting your current coil in the load side, the error introduced will be very high. As in the case of low power factor application, the current itself is very high for a given power. So that's why this is not preferred in practice. Let us go to the second connection. So here I am assuming this current again equal to current that is supplied from the source Is. So once the current reaches here, it will divide into Ip and I. So in this case, what happened? The current coil is measuring the current that is passing through your load plus current that is passing through your pressure coil also. So same thing I have mentioned, I plus current passing in the pressure coil, and voltage across pressure coil will be same as your load voltage. So same as V. Otherwise, the measured power will be, because the current coil is measuring the extra current, this current indicates what is the power consumed by your pressure coil. So that's why it will be true power plus power consumed by your pressure coil, or otherwise it is true power plus power consumed by the pressure coil. We know power is only consumed by the resistance. So I am assuming the resistance of the pressure coil is Rp. So this I can write as Ip square into Rp. So again here you can observe here. So the value of Ip is very high in low power factor meter, because we have seen in the last section, the value of Ip is nearly equal to 10 times the normal value. So that means we can tell that Ip square Rp there is a loss. But if you compare with the previous case, that means that type of connection that is made in A, in that case, I square Rc, the resistance of the current coil, there is some loss. So this I square into Rc, because current will be generally very high, that as displayed in figure A, that value is far high than the loss in the pressure coil. Or if the pressure coil is connected in the connected in the load side. So that's why this gives the less error compared to type A. Because the reason is the amount of the pressure consumed by the pressure coil is far less than the power loss in the current coil under lagging power factor conditions. So that's why the error introduced in the second method, or figure number B, that means connecting the pressure coil in load side, gives the minimum error. But let us assume I want to completely nullify the error. I want to remove the error completely. So in that case, we go for a compensating coil. So to understand the compensating coil, how it will be there. So your wattmeter will be changed like this. So there will be, this is my current coil. This current coil will have two coils. Let us take the two coils. One coil I am taking with the blue color. So another coil I am taking with some another color. Let us assume I am taking with the black color. So this is my another coil is there. So how this coil will be connected? This will be connected to this same coil here. So let us assume this is there. So this coil is connected like this. So let us assume this current is nothing but my supply current. So it is having two components. One component is current passing in the pressure coil, the current passing in the load. So this is passing in the blue wire. Which direction it is passing? This direction it is passing. So once it reaches here, this Is reaches here, it will divide into two. One is going to your load. This is nothing but I. Up to here, this is Is. Is is nothing but I plus Ip. So once it reaches here, this Is reaches here, it is dividing into two. One is dividing into Ip. So one current is passing here, Ip. Okay, the same Ip is passing in this one in the opposite direction here. That means the flux that is produced in the first coil, that will be proportional to Ip plus I, this coil. And the current that is passing in the second coil, that is proportional to Ip, but the flux produced will be in opposite direction. Because we know the MMF is equal to current passing through each turn multiplied by number of turns. So if I can make the number of turns are same in these two coils, they are wound in opposite direction, then automatically one flux is producing from left to right due to Ip, another one is producing from right to left. So both the fluxes will cancel each other, or otherwise the resultant flux produced due to current coil will be only due to the load current. So in this manner, the effect of the pressure coil current that can be completely nullified. So this is called as the compensating coil. So practically, if you are going for the low power factor type wattmeter, this compensating coil is used. So this current coil, I am just summarizing this. This current coil consists of two windings, each having the same number of turns. But only difference will be there, whichever the blue color I have indicated there, or the current coil. So that basically which is connected to your load, that will carry the load current plus pressure coil current. It should carry more current. That's why it is made up of a thick wire. Whereas the second one, because it will only carry the pressure coil current, so it is made up of the thin wire. But in order to produce the same MMF, what you have to do, both should have the same number of turns. And both should carry the current in opposite direction, so that the net flux will be only due to the load current only. So because of this, the error is completely nullified. So there is one more problem, compensation for the inductance of the pressure coil. So we have seen that due to pressure coil also some error is coming. So I want to completely nullify it. So how it is coming? Let us assume this is my voltage V. The current that is passing in the pressure coil, this is equal to IP. This angle is beta. This is nothing but equal to my current. So this angle is phi. So the value of the deflecting torque that is coming will be proportional to IP into, let us take this as current coil current, IC into cos of the angle between them, that will be phi minus beta into dm by d theta. So this beta, because of the beta, the error is being introduced. So I want to nullify the effect of this beta. That means I want to remove the effect of the inductance. How to do that? So for that, what I will do in this pressure coil circuit, so whatever the external resistance is connected, that external resistance is divided into two subparts, because that external resistance is equal to RV, total resistance, that is divided into two parts. So across one small value of the resistance, I connect some capacitance C. So what should be the value of the capacitance, so that the effect of the inductance is completely nullified? So that we are going to see. So before proceeding to that, let us see what are the different components that will be there in pressure coil circuit. The pressure coil circuit, the pressure coil will have the inductance L. Let us assume the resistance of your pressure coil is equal to Rp. Then it is connected in series with a series resistor, which is divided into two parts. The total resistance is Rv, and across which the capacitor is connected, that I am taking as R. So if you take the entire circuit total, the sum of all the resistance, that means equal to Rp plus Rv. That means the sum of small rp plus Rv, that I am taking as capital Rp. So now the total impedance of this circuit, so Z, I can write as the combination of resistances. What are the resistances that are there? One is Rp. Second one is Rv minus R, because I am taking up to here, plus there is a parallel combination of R and C. So parallel combination of R and C, and due to this inductance, there will be j omega L. I am just rewriting again. So the total value of the impedance of this parallel circuit, this I can write as j omega L plus Rp. This is resistance of the pressure coil, plus we have to take this much resistance, only this much part of the resistance. Total value is Rv. What will be this resistance value? This will be equal to Rv minus R. This will be Rv minus R plus, so the value of this R is in parallel with C. So this I can write as R is in parallel combination with, because of C, that will be equal to 1 by j omega C. So this I have to calculate. So let us try to calculate what will be the parallel combination of R and j omega C. So this part I can write as R into 1 by j omega C divided by, because R1 combination with R2 is R1 R2 by R1 plus R2. The same concept I am writing. So j omega C. So this will be nothing but R divided by, denominator this j omega C will come here. So j omega C R plus 1. So what I am doing, I am just multiplying and dividing the numerator and denominator with 1 minus j omega C, because I want to remove the imaginary term in the denominator. So what I am doing, 1 minus j omega CR in numerator. Denominator I am multiplying with 1 minus j omega CR. That means 1 plus j omega CR I am multiplying with 1 minus j omega CR. So what will happen? A plus B into A minus B is A square minus B square. So 1 minus, this will become j square omega C square R square. So j square is nothing but equal to minus 1. Minus into minus becomes plus. So that's why this will become 1 plus omega C square R square. Numerator will become R minus j omega C into R square. So this one I have brought and substituted here. So your total value is coming this. So now I want to remove this denominator term. So what I will do in the design, while designing the element, I will design like that. If I can design this omega says Q square R square, if this value is far less than 1, because the value of capacitance will be generally in microfarads, very small value. Even the value of the small r across which we connect also will be very small value, less than 1 mho. So that's why this value is very small. So then I can take 1 plus omega says Q square R square will be approximately equal to 1. So this entire denominator part I am taking as equal to 1. So only numerator part will be there. So I am just rearranging that. This I will become Rp plus Rv minus R plus j omega L plus R minus j omega Cr square. So here you can see this R and this R will cancel out. So your final equation will become small rp plus capital Rv. What is small rp plus capital Rv? You can see from the diagram, small rp plus capital Rv is nothing but equal to capital Rp. So this small rp plus capital, this will become capital Rv plus these two I am taking j omega common, this will become j omega into L minus Cr square. Okay. So now I want to remove the imaginary term completely. When this imaginary term will be equal to 0, when the value of L is equal to Cr square. Then in that case this imaginary term will go, impedance will be equal to resistance. What is the meaning of this? Your pressure coil circuit will become purely inductive. That means the value of the beta will be equal to 0, because we have seen in the last class derivation for error due to pressure coil inductance, error will be Vi sin phi into tan beta. So when the value of the beta is equal to 0, the error also will become equal to 0. And second one, the power that is measured will be equal to the true power only, because there is no effect of pressure coil inductance there. That phi dash or phi minus beta will be simply equal to phi. So that is the benefit. So these are the changes that are done practically. So I hope that practically how the low power factor wattmeter is designed, how it is different from the normal type of wattmeter is clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.